recording so that I can share my screen. And so we have a Raphael suggestion. Let me open this one. This card. Okay, so first of all, let me I let Raphael explain the idea behind his code.
Okay. So the project is to consider an environment composed of microalgae that can mutate and have new traits like their growth lesser or greater than the resident population. And the idea is to follow the evolution in the population of this new mutant population and show if it invade or not. And so it is the project.
Let's try to see how we could implement this model in netlogo. Okay, so this is the draft code that Raphael wrote down. So the idea is that you have some variable here for the moment. And so you set this variable to some value. Maybe then we can discuss about this. So these are equilibrium levels and so on. And you create a certain number of
defined by the equilibrium levels.
Okay. Okay. Equilibrium, this one.
Yeah.
And then you okay, they are randomly located in the world, and they have state resident and some color. So these are the number of resident. Okay, then evolution, you take one turtle with the state equal to resident, one with the state equal to mutant. For the moment, we have none.
Yeah, I think maybe it can make an error if there is no mutant at the beginning.
Should be no one, nobody,
Okay.
nobody. So we have to keep in consideration this possibility. So if so you extract one random number, and so with probability reproduce this mutant. So you create two new turtles, no? One new turtles.
At the beginning, I create two, but the resident remain on the
Yes,
population, so
sure.
there is only one.
Okay, but maybe this could be an action done by the resident. So especially if you want to say model growth of a colony, in some special. So maybe this could be ask R. No?
Yeah.
And in this case is hatch. Turtles one. Hatch is like to lay an egg, no?
Okay.
Because the idea is that if is a patch that creates a turtle, it is sprout.
Okay.
It is like, it's arising a plant from the ground. If it is another turtle, it is hatch. And if it is the observer, it's create. So you are the god.
Okay.
Okay, so in this case, this could be clearly, we could, for instance, also add a genotype to these animals.
Okay.
No?
Okay, we can But maybe it's a little bit complex.
Let's finish this and then we may play eventually. And eventually with another probability mutate, no?
Yeah.
So you create one turtles set. So this again can be like some ask r, no? Hatch turtle, no hatch. It's simply hatch, not turtle. Hatch one, no? Set shape circle, etc., etc. Okay. Otherwise, it dies. Okay. Resident out. Okay. So this could be the beginning. So let's play a bit with this idea of genotype. Let me think. Now, in order to so for the moment we can save this. Let's try to make a toy model with genotypes.
Okay.
So let me try. So say pet and turtles on genotype and maybe also phenotype.
Okay.
So maybe genotype. We can add a slider, say genotype length, no? Say from 3, say to, I don't know, 20. So this is the number, the length of genotype. We can use Boolean genotype, say zeros and 1. Then we may have some compute phenotype function, and we pass a genotype. Okay. To report. And then, so this can be just to compute the phenotype given a given genotype. For instance, for the moment, we can just say report sum of G, the number of ones. Okay. So this for the moment. And so this is another could be to survive of a phenotype to report. So let me, this is just to say, compute phenotype given a genotype. Compute probability survival of a phenotype. Okay, we shall compute something here. Okay. So we have to do this. Then, okay, maybe another is to report mutate G. Reports a mutated phenotype. And this could be, I don't know, for instance, this could be a nice problem. The catastrophic senescence of salmons.
Okay.
Do you know the problem? The fact is that all salmons only reproduce once in their life, and then they die. Okay. So the idea is, let us try to develop a model that shows that if they have chosen the strategy, the R strategy, the ones of producing as many sun as they can, it is useless to survive to the first reproduction phase. So I remember, I'm trying to remember one of these. So the idea is that we set up in age, the first reproduction age. So from, say, 3 to, I don't know, something. First. So this was, let me see, let me show you Penna model, I think, Penna model catastrophic senescence. Should be this one. Catastrophic senescence of the Pacific hormone, no? And so I think it is this one, or yes, should be this one. If I remember, so let us put this on the notes so that, okay. Okay, so the idea is the following. Each salmon, for the moment, let also breed salmons, salmon, so we can use a more interesting way of addressing turtles. This is just another name for turtles. So,
and there is no difference between turtles and
no. The idea is that if you have more breeds, you can address separately one of salmons, one of, I don't know, frogs. Just for practicing with another way of calling a set of turtles. So salmon own genotype, phenotype for the moment we do not need in this case, but age yes. So salmon are giving birth at age equal to 0, and then age increases by 1. If at each age, one bit of the genotype is activated and can be 0 or 1. If it is 1, it is a bad gene. And if you accumulate, I don't know, 3 bad genes, you die.
Okay.
And of course, so okay. Then if there are enough room, because you also have to yes. Okay, so someone is asking to enter. Let me see. Okay. Hi. No. He has tried, but something didn't work. Okay, now yes. Okay.
Yes.
Are you here?
Yes, I'm here.
Perfect. So we were discussing a model that I shall present you. If you have questions, please interrupt me because I do not see your window. Okay. So let me share my screen. Please shut up your microphone because there are noises. Okay, please. Let me see if I can mute them. No. Here? Oh, yes. Maybe here I can. Where? directly here. Okay. 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 I muted your microphone because there were noise, but if you need, you can reactivate it. Okay. So let me continue. So the idea is this following one. To try to model this article, catastrophic senescence and semi-parity in the pen aging model. So the idea is the following. The Pacific salmon only reproduces once and then it dies. And so this model tried to develop a simple, say, representation, a simple model that could reproduce this. The idea is the following. Salmon has a given genotype, a string of bits. At each age, they activate one of these genes. If the genes can be 0, which are good genes, or 1, which are bad genes. And so if they activate, I don't know, we can put it here. The death gene number, say from 3 to something. So maybe if they activate 4 bad gene number, say bad. Oh, this is the limit. So the death. Okay. So if they activate 4 bad genes, they die. Okay. So let's. Yes.
So I don't know. I'm not understand what the. I'm not understand this. What you say? Is it an exam or what?
No, so this was the last meeting, the last lesson of a course about using this platform called netlogo. I've sent you the page where you can find the other lessons, and in this site you can also find other courses about how to use this platform. I
Okay.
put again here in the chat. So clearly, if you participate only to this last lesson, I fear that you will not be able to produce. But if you want, you can. I can try to illustrate the idea of how to develop a visual model using this platform. But this is not an exam.
Okay. I'm understand.
So if you are not interested, feel free to abandon it. I'm not recording presence or other. Okay.
Okay.
So the idea is that netlogo is a platform for simulating agents that I don't know, move, interact, modify tasks. So for the moment, we are trying to develop a model in which you have a certain number of salmons. Then I shall show you. Salmons have a genotype, which is a string of bits, say 0, 1, 0, 0, 1, 0, 1, 1. Okay, so clearly this is the gene activated at age, say, 0. This is the gene activated at age 1. Then includes, so this is age 1, age 2, age 3, age 4, age 5, age 6, 7, and so on. Clearly, if they arrive at the end, they die. So essentially, this is the maximum age, essentially. But if they activate, say, 3 bad genes at a certain age, they die. So that, and then they can reproduce only if they arrive at a certain age, say 6. So the idea is that by selection, we should not have in the population any salmon after a certain number of reproductive steps that have 3 bad genes below 6, because they cannot reproduce, they die before reproducing, so they are eliminated. But the question is, how are bad genes distributed beyond age 6? So are they distributed, say, more or less randomly, so that can be also salmon that reproduces at age 7, at age 8, and so on? No? Or they all have one bad bit at age 6 and 2 before, so that when they arrive at age 6 or at age 7, they reproduce and then they die. So the idea is to look at the by selection the distribution of genes in the genotype. So we shall produce here a plot saying how this exactly. So this is the idea. So hormone has a genotype and age. Okay. So let me for the moment remove this, because otherwise. So to set up, we shall ask to a certain number of cells here to give birth to a random salmon. To set up, ask turtles. We can also have just a few of them. Turtles, say, with random flow at 1 less than, say, 0.2. So it is about 0.2 of turtles.
Okay, but you can directly call salmon or
salmons.
Yeah, okay.
No, these are not turtles, patches. Say, sorry me. I want to each. I want to select. So patches is the set of all patches. The patches are pieces of field here. I ask all of them to compute this, and only those that return that have this true survive. So are selected. So certainly 20% of this turtle will will be activated. Then they sprout one, no? Tarto, salmon, sprout salmon, sorry, sprout salmons, one, fish, I hope there is a fish. Set color random, okay, this is not, set genotype, then I shall put here, set age 0. Okay, this is more or less the idea of generating salmons. So genotype, I use n values, and values I can show you what n values is. A netlogo dictionary. So n values is something for generating a list of a certain number of items. So we can give an anonymous function, an anonymous reporter. So for instance, if you gave a constant anonymous reporter, it returns a list of 5 ones. If you give the identity reporter, it gives 1, 0, 1, 2, 3. Now, or if you put here a random something, you can generate a random string. So this is n values genotype length, this one, of what? Of x, which is just a placeholder, random float 1, and let's say if else value, random float 1, 0.5, 0, 1. Okay, let's see if this works. No, I already this. Okay, check Solmons, check. Okay, let me save as Penna model. No, this one. Say Penna model. Okay, so I have also to have a button set up. Okay, so we have a certain number of fishes. Actually, in English, there is no fishes, but no, fish is plural.
Oh, yeah.
A certain number of fish, which is for me it sounds quite bad, but okay. And so you see that this is its genotype.
Okay.
And okay, so these are the, and so now to go, so we can ask Solmons. First of all, we increase age, set age plus 1.
Okay, yeah.
If age greater than genotype length, or now we have to sum. Let me define a function in order to keep things compact. So to report phenotype, phenotype is the number of bad genes.
Okay.
Phenotype of G and the age. It is the number of ones, before A. So we can use the reduce. This applies an anonymous function again, and takes the first two. So this anonymous function. So it takes the first, applies this anonymous function. Then no, okay, no, I can take two.
Okay, I understand what the function.
Okay, so it takes the result so far and the next item, and then you can define which operation you want to. So
just the size of the list by sum or.
So for instance, we can report reduce. So sum item into S plus if else value. No, because I would need to count how many. So because I have to count, no? Clearly I can produce a loop, do this. I'm trying to do something more sophisticated. So let me do the following things. Map can take up to can take many lists, and but this is a very complex way of doing this. How I can maybe I can just take the substring. So substring is this substring list position 1, position 2. So this is very simple in this way, because I just take return report sum of substring G 0A.
Okay, from 0 to okay.
Substring from 0 to A. So this is quite simple, no? So, or age, no, or this one
equal to
greater or equal to that gene number. Or please, the problem in that actually calling a function in Lisp, it is done by constructing a list in which has the function as the first element. So if it is, since netlogo tries to not to put too many parentheses, if you have just an element, you can just write a sinus of x, which is exactly the same as writing sinus x.
Okay.
But if you have more than one element, you have to put the parentheses.
Okay.
So if age greater than phenotype length, or phenotype of genotype age, because we are asking Solmos, so we can access their variable. So we pass the genotype and the age. Greater than this, die. You can write this like this. Okay. Why? Okay, something was okay. Otherwise, we can do this if else, but it has already died. But just to be clear, otherwise it reproduces.
Okay, if it reached the first reproduction age.
Okay, yes. If age greater than first reproduction age,
greater or equal, no?
or equal.
Because it's the first prediction age.
It is so like this.
Okay.
Let T1 of patches ask T if not any salmons here. This is the fight for space. If it is not salmons here, sprout salmons 1, set shape fish, set genotype mutate so it would be genotype of myself, but instead of putting this, I prefer to let G on my genotype.
You give the.
I just copy the genotype in this list because now I'm talking to a patch.
Okay, but it's the genotype, the parental genotype.
Yes, this is okay. Parent genotype.
No,
Let's parent genotype because this is the salmon.
Okay.
No, so salmon say okay. Instead of putting some strange things like genotype of myself, which is not very clear for me. Now mutate parent genotype.
There is a P.
Parent genotype. This one. Set age 0. And that's, I think it is enough. Then we have to define this mutate. And we may say use a slider for mutation probability. Say maximum 1. We have to define this, or if we want, we can add. Either we can have always mutation and here set how many genes they mutate, or mutation probably per genome or per gene. Let's suppose it is per gene. So we may keep this quite small. Maybe we can also a maximum 0.1 because it generally has no sense to have. But we can also see what happens if there are a lot of very high mutation rate. There should be a certain time they should die everything if you have a very high rate. So let me to report mutate G. And so we can report for each, I never remember for each the order of arguments, for each list command, so for each G, then X in if else value random float 1 less than mutation probability. So it's 50 gene. So, or we can also have just bad mutations as you want. Normally, this is done also. In general, the idea is that a mutation. So these genes are not bits; they're very big. So if you have a mutation, generally you inactivate the genes. So for instance, yes. So if else value say x equal to 0 and this 1, otherwise it stays 0. You should see. Because the mutation probability is not 1, so some is still keeping the all genes to escape. So the idea is this one, even though you only have a bad mutation. So if in this sense, the idea is that you activate genes, but if you have a mutation in these genes, it's very probable that in the coding, in the important part of the gene, this is generally inactivated. It's very bad, very rare to have a back mutation to a working gene. No? So let me see. See, yes.
My battery is low, but I'm not at home. When I arrive, I will be
Okay,
reconnected.
in any case, you can see the lesson recorded from that page. Okay, if you have to go.
Okay, thank you.
Bye. Okay, so if not, sprout salmon, mutate parent genotype, set age 0, that's all. So we may also remove C, we don't need because it's quite clear. So we can write here only bad mutations. Okay, let's see if this works. So if age greater than first reproduction age,
Just for the report mutate. Okay, no. If x equals 0,
so
okay.
it has to be at 0.
Okay.
And with probability, some mutation probability, it becomes 1. Otherwise, it stays at 0.
I missed the x equals 0
Should be.
part.
Now we can test, closing bracket expected, to go, this is not, okay, so first of all, let me save, then we can try. So mutate 0 1 0 0 0 0 1 0. Mutate, something is not, some expected to be a list, but got, substring is sublist probably. Sublist, it has the same syntax, but so
okay,
sublist. A string is just a list of letters. Let me see now if it is works. If it is, so mutate, no, still something. Report expected one input. For each G. For each G, yes. Why is not, it doesn't like it. For each, because for each, no, runs the command for each item of the list. Commands, because it is not a reporter. So it is, because for each it takes, should be map. So it is map, but for sure map has the opposite syntax. Okay, because yes, because map takes a function and the list and returns the function modified.
Okay.
For each executes a command for each element of the list.
Okay.
So let's see if now it works. We shall save before. So mutate. In this case, it is a completely, no. So if else, yes, because we have to, if else x equal to 0 and random float this, otherwise it has to stay as it is.
Okay.
Otherwise,
Okay,
no, because here, okay, here now if I put the mutation probability, okay, sometimes now we have a bad mutation. Okay, then let me see if I have a phenotype of say 1 0 1 1 0 1 0 0 phenotype and age 3 2, no? Okay, because 0 1 and 2 and sublisted from 0 to A. I think A is excluded, no, from this, because otherwise.
Yeah, because it's 0, 1, 2, 3, and not 1, 2, 3.
Because you see now if okay, it should be from 0 up to before this, but it's not really important now. Okay, so setup. Okay, clearly we have to start with the clear all, otherwise. Okay, we can also reset ticks, but it is not really important. Tick. So setup, and then we have to go. Okay. You see that now things are evolving. Let me see. If I increase a lot of mutation probability, I should see some catastrophe. Okay. So this is already, this is a kind of mutational meltdown. Oh, now let's try to plot the distribution of genes inside the genomes. So let me display distribution.
You can follow, it's a structured population, so you can follow each
as you want, but each the genotype of one of these doesn't mutate.
Yeah.
It is only offspring who mutates.
It can be interesting in terms of study to see the distribution of age class in the population to see.
Yeah, sure. So we have to select. Well, for the moment, let's start with the distribution of this. No.
Okay.
So the idea is that I set up a list of say genotype length. This could be also some globals distribution. Then I set distribution and values 0 of genotype length. Then I ask Solomons to for each this time, for each, no, set, because I cannot alter a list, I have to set the distribution map x sum x, say, in S plus x of distribution genome. So the idea is that I pass to map distribution so far and genome. It takes one element from this, one element from this, and they sum, and they are put at the same position. So it is like a vectorial sum of distribution and genome. This. Then clear all plots.
Okay.
And then for each distribution, I use for each plot x, plot x. Okay, someone is asking to enter. Lucille. Lucille?
Yes, sorry, I'm very late.
Oh yes, you missed the a model, but I can try to show you what we did. Have you progressed in your approach about simulation of absorber and so on?
Yeah, just a little bit. I saw that you sent me an email saying that you added like the thermostat on the substrate.
Yes,
So
and
I was looking at it,
I
but
also
I
added
was
another thing. But first of all, let's finish with Raphael
okay.
project. So we are doing a completely different things.
Yes,
But
sure.
so the idea is the following, Lucille. We are trying to model this paper, if I remember well, because I used it, but I've seen a seminar on it, say, some 30 years ago. But let me see if I can find this one. Catastrophic senescence and semi-parity in the pain aging model. The pain aging model is a very simple model trying to show the accumulation of bad mutation in a population. So the idea is the following. We have a yes, we have to finish this. We have a certain number of turtles, which we call salmons. Mm. Each of
Okay.
them has a genotype, which is a string or a list of genotype length ones or zero. Zero are good genes. Ones are genes that have at least one bad mutation, so they are not working. And these genes are activated each after the other, given the age of the salmon. So I mean that at birth they activate gene zero. After 1 year, they activate gene one, 0 and 1. After 2 years, they activate 0, Z1 and 2, and so on. Mm. And so, okay, so we generate salmon with a certain shape, with a genotype, which is just a random, say here, 0 or 1 with a certain probability, 0.5, okay? Then when they go, they increase the age, clearly. If the age has greater than the genotype length, or the this function that I shall show you in a moment that counts the number of genes activated is greater than this death gene number, they die. And this function is this one, very simple. It takes the list from 0 up to the age. I'm passing here genotype, which is this, and age, which is this, and sums the number of ones. So that and sums everything which is there. So essentially, it counts the number of active genes which are 1 from 0 up to age A. So if you in this case, if you are age, say 4, and you have 2 genes, so let's see here. This is a genotype, possibly. This is an age, and phenotype counts the number of ones up to this age, up to and before this age. So 1, 2, 3, 3 in this case. If I put this equal to 2, just 1, because this is the gene, okay? And otherwise, if they are older than the first reproduction age, they can reproduce more than once. The idea is to see how the seminal parity, so the fact that they only reproduce once, arises from this, okay? So, if they survive, so if they have the reproduction age, this is just for saving the genotype of the parent, and then they choose one of patches, this makes also a constraint on the total number of salmons, otherwise they can increase exponentially. If there are not any salmon there, then the patch sprouts, so generates a salmon with the genotype of the parent mutated by this mutation probability. With this mutation probability, mutation is this one. Set age 0. Now we want to distribute the distribution of genes in the population, but probably this is not the best thing to do. We should rather plot the distribution of the age for which they have the death gene number of genes activated.
Okay.
So the distribution of death times. I think this is better. Now, since this is independent of age and so on. So the idea is that we ask all salmons to find the distribution, the death distribution age, which maybe we can write down to report death age. So we let's say maybe we can just report reduction, report report what? I think this is a kind of a usage of this reduce function.
Okay.
Because it starts from the beginning, you know, and so it takes the first two, and so on and so on. So
you take
the
genotype of each individual and see where at each age it can die.
Yes, exactly. So let me let's try to write this. I don't know. Report reduce. How is the syntax? Reduce is you take an anonymous function with two items and the list. So reduce x and y. Then if else value returns x less than death gene number, I have also to associate an age. Maybe we can just let a 0. Let me see if it works. If else death age, but I cannot do this with an elf. No, this is not working like this. Because I should count. I'm pretty sure that it is not working. Let me say if else x less than age set a plus 1 x plus y I'm pretty sure it is not working. Yes. This is a check. Expect a literal. Now, because here it is it wants a report. So I'm trying to write down a report with a side effect, but it's not really liking this. But first of all, there is this. Let me see. Reduce expected two inputs. An anonymous reporter. This. No. But this was checked. No. So here, if no, so okay. So let me do another thing. So first of all, we produce the cumulate of this, no? So not reduce. But let's try with a for each. Since for each, say let age 0 for each. So for each takes this, let add 0. So for each g, x in s set ss plus x if s greater than that gene number set a set s plus it. Set a plus 1. Set ad equal to a. But if s greater and ad equal to 0, because otherwise I set for all the rest, no?
Yeah, it would continue to.
For each. Okay, report ad. Let me see if this works. Check. Set export. Set ad a. Check. Rather n values. N values was not like this. N values. First the number and then always because I don't know why sometimes you take first the least and then the there should be some okay, let me see. Genome ask salmon set distribution. Why genome?
Genotype, no?
Genotype. Genotype. Okay. For each distribution. For this. So let's try to find the show and death age of this. Maybe we can add some more one. The age 9 0 1 2 3 4 5 6 7 8 9, but that gene number is 4 for each G. If S E
it's not +1. No,
X.
X.
Show. Let me check. Show X. So it is 1 0 1 1. So this is going okay. No, it is reading this. So it increases X by X. So show. Let me say. Show word X S. So 1 0 1 0 X S is equal to 1, no? Poi it reads 1 1 1 2. Should be this seems to work, no? So S is the accumulated if set A plus 1. If S greater than that gene number 4, and we have not yet set a D.
It's because it's superior and not superior equal.
No, I don't think, but let me write also. So S A. So 0, no, 1, then 2, 3, no. This is increasing. Age, okay, this is increasing. When 6. 1 0 1 2 3 4 5 6. 1 2 3 4 5 6. Should be, no?
It's okay. 4 gene.
So let me try with another example. If I put a 0 here, should be give 7, no? 1 2 3 4 5 6 7 at age 0 1 2 3 4 5 6. Actually age should be 1 less, but this is not really important. Okay, so we can remove this.
Okay, because it will begin at age 0 and not
yes,
age 1. Okay.
But it is not really important. And so display distribution now. We should ask salmons set this is quite we could simply if I do something like plot if I write a histogram of histogram and death, age, genome, of salmons, there is something wrong here. Set up.
As a genotype.
Genotype. This should more or less be, no? So we can just copy this here. We add bar. Okay, so this can be left here because we don't need them. And now let's see what if go. No, set up. Go, no, something which is because I have to set up forever. Okay, so you see that there is a concentration. Actually, probably we have some shift, but let's try. If I increase this, yeah, it should go to X max. It should be 20.
Okay.
So you see that the starting, so essentially they're almost clean here. Nobody clearly here before 6. And so now one can play with this. So the first reproduction age, now this could be less than the first reproduction age, I think, no? So first reproduction age is 7, but clear now I have to check if the numbers we are missing one.
Okay. Yeah.
So actually, I remember that this should go quite sharp to 1. The problem is that I don't know. Let me put this cancel. No. To put this in some. So first of all, they reproduce. Ask salmons. It should be the same because it is executed when you have the tick, but we can put this here. It should be exactly the same. Actually, not really. It should be more sharp, the threshold. Clearly, the problem is that I should, maybe I can put this here. Because first I let all of them die, no? And then, because I fear that it is the reproduction phase that alters the distribution.
Okay.
maybe, yeah. So if age asks salmons at the point that they are all died, all who should not reproduce, no? Worse than why I have this big peak here?
Yeah,
Because if age greater than genome length, no? Or age or phenotype greater than that gene number die, this should eliminate all salmons. So I don't understand why here I have, now it disappeared. Probably here we have some one less than the ones that we have seen here. So this should be 7 probably, not 6, not 8.
Okay. And you cannot change that by removing 1 to 80 here.
There is something strange. Now we have 10 instead of 7. Okay, I don't know why. You should check a bit this. In case this is a way of.
It's not because when you generate genotype, there is 50-50.
No, but only at the beginning. Only at the beginning.
Yes, after that.
They are eliminated. So we can see what happens if we increase the mutation rate, for instance. Yes, probably this is also.
Okay, it's because there is 2. Oh, okay.
You can reduce the maximum. It seems quite, but let's check the paper. Maybe I have wrong. Okay, we should revise, but essentially here is yes, we could just simply plot the population age.
Yeah.
Let's see what happens if we plot instead of this. We plot the population age. Where is here? Instead of this, we can histogram age of salmons. They survive 5. if I put this less than this one. Okay, in this cannot, they die because they cannot have a 7 before this, no? And here, a lot of survival. And if I reduce this, we have still, well, I don't know if this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, it's about 9. The first, the drop down, so the drop of the reproduction age. Okay, in any case, you see that the bad genes accumulates the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I don't know which something is not really work. You shouldn't behave like this. Here they can accumulate a lot of bad genes because this is not really very important. You see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, probably we have to if age greater or equal to first reproduction age, yes, probably. Actually, one is out of here because they start at age 0. Then, but when they arrive here, they have age 1, so it is okay. Because they are okay. This is good. But okay, in any case, this is. Now the other thing is that probably there are too many fish here. Let me reduce this so that we have less fish surviving, but doesn't seem to change very much. Because I remember that there is also the problem that if you don't let the population evolve enough, you don't have a great variations, but it doesn't seem to change. Okay, we have to inspect better this, but in any case, it is an interesting. No, we have seen a lot of different functions. I tried not to use the iteration as we. I think I prefer to do just a 4, no, and count and things. But this is not the spirit of this language. Okay, Lucille, I came to your
Yes.
problem. I also did another variation of the multi-particle collision dynamics.
Is it the microcanonical?
Oh yes, the microcanonical.
Because I tried to look at it, and there is a few things I didn't understand.
Yes, let me see. Let me show. If now we come back to physics. So the idea of the multi-particle collision dynamics, which is this one, is very simple. Now you, where is the code here? Each particle has the position, the velocity, the mass, and the kinetic energy. We can okay, this is just for setting up the boundaries. In this case it is the whole lattice, but then so that we can reduce it to a space in order to have other effect. But here they're not really used. So I now, this is for the moment, this is just commented. So I generate all particles with the same absolute value of the velocity. It means essentially with kinetic energy equal to 1/2, no? Because m is equal to 1. This is a cosinus and this is a sinus. So essentially 1/2. So k, I don't remember why k, because probably I have multiplied it. I have not. Yes, it is a sum. Okay, over 2, but not really important. Actually, I think I'm not really using this k. Okay, so essentially you let particle advance for freely without seeing other particles, and then maybe bounce on the boundary, and then the collision are performed by patches that if there are more or equal to 2 particles, then they compute yes, here this histogram is not really working because I'm not updating the. Let me see. Let me remove the kinetic energy and compute just the kinetic energy. Yes, but actually this is here. It is the no. Okay. Let me compute the kinetic energy. So Vx square plus Vy square over 2, maybe m times. And the problem is that these collision dynamics do not change the kinetic energy sum. I don't understand what is not sum Vx square plus. Okay, the problem is that this. Okay, so this is not changing, but worse is that it is not changing for all particles, because essentially, clearly, if you have 2 particles, you just rotate them. Now, since it is in respect to the center of mass, they are the same length. So if you rotate, they do not change length, because the fact that they have to conserve the x and y component of the momentum, they cannot change. With 3 particles, we could, in principle, change the velocities, but not simply by a rotation. With the rotation, you keep all components the same. So, okay, Lucille. So I found in literature how to couple this with the thermal reservoir, but this is not a microcanonical ensemble.
Just I have one question, because you opened the MCD file, but the one I saw was called MCD microcanonical. What's the difference?
This is the original one, without.
Yeah. Okay.
Okay.
Oh yeah,
Now,
without. Okay.
Okay. Now I thought that we can simulate the microcanonical ensemble, which means conserved energy. But the trick is that instead of conserving energy, I let energy fluctuate just a bit, so that essentially there is a small, not a large one, a small reservoir coupled to this system, so that when after doing the rotation or before, I can alter a bit the length of the arrows, of the speed of the length. So the idea is this one. I propose a change of energy of the order delta E, which is small. If in the reservoir there is a space for this delta E, which can be positive or negative, then I alter, or now I shall explain, I alter all velocities. And then I update it. The other problem is that I don't want to have a common reservoir for all patches, because otherwise I can have a transmission of energy instantly from one side of to the other. So, for instance, I could have just a single reservoir coupled to all system, to all patches. But in this case, if I can remove a small bit of energy from this, and this can be used by by particles in the other side just to increase the energy. So I put a reservoir in each patch. So essentially, this is the energy reservoir of this patch. And so here I say, okay, so delta E is some value, some small value. I can put 0.1, say, something like this. The local fluctuation of energy. So I propose a fluctuation of up to plus or minus delta E. If energy is the reservoir of of this patch, can be positive or negative. I sum this, and this can be positive or negative. If they are not below minus delta E nor above delta E, I accept this. So I try to accept these changes. Then I take the pH is particles here. I just computed these ones. I don't know if it is smart enough that if it finds the same expression in several places, computes again this or not.
I try to understand because it's totally not my field of study. But
the idea is this one. So in say statistical physics, you are studying a system composed by many particles. Okay. In principle, if you think of a closed system, in principle, energy should be conserved in collisions. And then you may, so this is a problem that was studied by Boltzmann. So the idea is that can they reach equilibrium? Equilibrium means a distribution of energies like the Boltzmann distribution. So x to the minus something temperature. If you perform the real dynamics using small time steps and the Newton forces, this is called the molecular dynamics, it works. But this is extremely slow as a method for doing integration. So people have tried to find a quicker way of performing simulations. This is one. So clearly this is not a Newtonian dynamics, since a particle can pass through each other without interacting in one small step. So then this kind of interaction can be shown that it has certain positive things. So for instance, they destroy correlations quickly. Clearly, if particles go simply without seeing each other, the correlations remains the same because the initial distribution is not altered. if they interact in this way, actually there are some nice property. For instance, if you start with, say, half of the gas at rest, and the other which is essentially going this direction, after a certain time, all the fluid is going in the same direction. So there is a kind of viscosity. So no, and so on. Okay. Now the problem is, can we have also thermalization? I mean, redistribution of energy so that the total energy is conserved, but it approaches the standard energy distribution that you expect from the statistical mechanics, maximization of entropy, so second law of thermodynamics. This is the idea is always the same. The second law of thermodynamics says that entropy should reach a maximum. And in order to this, you can easily show that it should have an exponential distribution, which is the Boltzmann distribution. See, but this dynamics does not this because it conserves strictly the energy of each interaction, not just the sum of the energy. So now I said, okay, this is a trick used in several places. The problem of this is that it is difficult, given a local configuration of these particles, it is difficult to find another configuration with exactly the same energy, exactly the same Vx, and exactly the same Vy. No? Because so you could do this, but you have to, say, extract random numbers and try. So the idea is that, okay, let it, so the conservation of momentum is quick, so is easy just by the rotation. You have this conservation of momentum. In order to have an average conservation of energy, but not a strict conservation of energy, I let the energy be absorbed locally or released locally, but only with small fluctuations. So instead of having a strict the motion on a surface of strict energy conservation, I let the motion move in a small cap, no?
Okay.
So exactly. So I compute a possible fluctuation of energy, local fluctuation of energy of the from minus delta A to delta A. If there is a room in the local reservoir for this fluctuation, I try to apply. So because I computed the total energy of the particles there. pH is particle here, no? Now, clearly, I cannot reduce the kinetic energy below 0 because it is strictly positive. So if this fluctuation is less than the total kinetic energy, now I can proceed. Otherwise, I don't do anything. No? Now, if you see that if I want to have the new energy equal to the old energy plus dA, you have to multiply the energy by this factor. Because if you multiply this by a tot, you have dA plus a tot. So this is also, and since the energy is the sum of x squared plus vy squared, you have to multiply each velocity by the square root of this coefficient alpha. I think this can be, well, we can leave or thrown away, I don't know. Okay, so now you see that after a few interactions, the distributions of energy of the particles follows what is expected. even though I think that we can reduce quite a lot the fluctuation. Let's see. You see that it is essentially independent of the fluctuations of energy. Clearly, if they are extremely slow, I think that they can take a lot of time in order to, well, not so many, in order to relax, so maybe we can try to add some other zero here. Okay, so, but if you now look at the total kinetic energy, essentially it is constant, even though locally it can fluctuate. Actually, I think that this is sum of square. I should be plus some energy of patches, which is essentially zero because it is this one. So this is the total energy of the system. So, and this is strictly. Now, clearly, if I instead increase this, now the total energy stored in the patches fluctuates a bit. These are, but essentially very, very little. This is sum of particles plus some energy of patches divided the number of patches. I don't understand why this is not the constant. This is well, there is always something. Okay, setup is 4. Should stay 4. If I put this setup, this is 4. Here it is almost 4, but I don't understand why it is not strictly 4. Why? Because the exchange should be 0, because I multiply each by square root of alpha. So Vx square plus Vy square is alpha times all the energy. Alpha times energy. Ma chi è che mi rompe quello? Alpha, but something is not still understood. But Lucille, have you understood the idea now?
Yes, thank you. That's what I thought, but I wasn't exactly sure.
No,
I still have some difficulties with the code.
Yeah, sure. And okay, so let me know if you want to try to implement something with this or the other model.
Yeah, actually, I had a question. Is it possible to implement like an energy distribution, like a probability of energy level for a quantity of particles?
Just let me know if this is someone really looking for me. No, they're all different, so I think that they are just spam.
Yeah.
If it is always the same, it may be, no, but if they're all different. So let me understand, Lucille. Can you try to say write down something or?
So the thing is, what I'm trying to modelize is not exactly like a gas. It's more like the photons of the sun. And so for each wavelength, they have like a different energy. And there is so a proportion of photons with each energy. So I was wondering if it's possible, for example, to implement this kind of data inside the code. It might be difficult. Maybe it would be possible to call for an external source or something.
No, but the idea is that you want to generate something from a given distribution.
Yes, like for example, if we take the current simulation, what I would like to try would be to have like some of the particles we would have like one energy, the other would have another one, like to have the full distribution of the sun energy, for example.
Yes. So, but let's start from scratch. So suppose
Yes.
you have the black body spectrum.
Yeah.
Hmm?
Yeah.
And you
very
want to generate something with this from this distribution. This is the idea.
Yes.
So the general tool for doing this is a kind of Monte Carlo, essentially. So we can. I should try to remember because I have used these three.
Sorry, it might be difficult.
No, not difficult at all. But there are some you have to remember a bit. So essentially, we can do Monte Carlo with direct sampling or with say random walk sampling. The idea is the following. Yes, because the problem is that you have an infinite domain of frequencies.
Yes.
So you cannot simply do. So let me try to. I don't have anything to write down. So let me try to use a Jamboard if it is still present in because
It's not.
No, it is still for some months. So I can just.
I can't see your screen. So.
Eh?
I can't see your screen.
Yes, now I share again my screen. Now you can see.
Thank you. Yes.
Okay, so let me start. So essentially, I have this is my x, and this is my probability p. And
Yes.
suppose I have some curve like this, no?
Yes.
So the idea, the simplest idea is I bound this by a rectangle. I choose an x, say this one. I draw a random number from this to this in this interval here. If it is here, I don't do anything. If it is here, I emit the photo with this frequency. So this works, but in this case, it is not really very interesting because this curve actually it is not like this. It is more, say, like this. So it has a very, very long tail of very, very small values. No? And so the problem is that you throw away a lot of efforts of generating these values here.
But if we know the proportion for each small interval, maybe we can just implement them directly.
So the second possibility is to have a function that you can easily compute in a certain sense, and that approximates your curve. And so now, you are generating it this way. But there is another way, another possibility is that of using importance sampling. So the idea is that this is your probability distribution. No? So suppose that you have emitted a photon at a certain frequency x, no? Which has a certain distribution p of x. Now you propose a change of this to y, which corresponds clearly to a certain probability p of y. So you want to accept or not accept this with a certain conditional probability y given x, so that the asymptotic distribution is this one. So I mean that I don't want to compute directly this, so to extract random numbers like this. I want to say, okay, this is my x. Now I propose to change x to something y. Shall I accept this or not, this change or not? Clearly, the idea is that if I'm going where the probability is higher, I accept preferably the movement. Sometimes I also accept the opposite movement. This is the idea of Monte Carlo computation. So, and you want that after having done a lot of variations, your total probability distribution is the one that you want to have. Now, how can you compute the tau? The idea is that the flux between two maybe this, let me change the color. That you assume, you compute, so you fix your attention to this interval here, and maybe to another one here, this one. The idea is that the probability of going from here to there with respect to this one should be equal to the proportion of these two things. So these two things, in order to have a stationary solution. No? So the idea is that if there is a small probability here and a large probability here, you should also have a large probability of going from this to this and a small probability of going from this to this. So this is called the tailored balance, and so says that tau of y given x divided by tau of x given y is exactly equal to p of y divided by p of x. And so this is extremely useful when you perform simulation in statistical mechanics, since you know that p normally is some normalization constant, no? Exp, as we have seen before, of minus energy divided by temperature. This is the Boltzmann distribution, no? But this is the difficult part in the Boltzmann distribution, because this normalization constant is the sum of all of this over all possibilities, no? Because you have to have the integral of p is 1, no? But normally you have an infinite domain, so you don't want to compute this. And this clearly avoids to compute this, because you don't need to have the normalization factor. So let's try to see if this works. So the distribution factor that we want is, I don't remember the black spectrum, x to some power, I don't remember which one, exp to minus x, no? over t, and this is x square. I don't remember the black body distribution. This one. Yes, it is cube. Okay, we can divide it by. We can approximate in several ways. So this is energy density, which is essentially the energy, no? So it is essentially x to the third divided by this, which okay, we can use this. This is clearly when you can throw away this one, you have x to the minus energy divided by t. Okay, so let's try to, first of all, let's check this is working. So new plot, if I set x range 0, I don't know, 100, plot x to the third divided by x over t plus 1, clearly t equal 10. Okay, so this is the black body, no, at a certain temperature. Let me add, say, replot, no, set t equal higher temperature, and no, I have not found. Okay, so let me define a function. So p of x given in the t is this one. Maybe I have to put an equal. Okay, so plot p of x 10, p of x 20. Okay. It is not normalized, but we don't need to normalize. But the normalization, it is -1, first of all. Otherwise, they are fermions. Let me see again. So they shouldn't. This -1 doesn't change very much. One is not really. Maybe 1 is too small. Okay, it is here. We don't see. And then clearly they should be normalized, but I don't want to. I don't need to normalize them. Okay, so let's try to implement a new what? Okay, let put here a temperature slider t, say from 1 to 100, and okay, maybe some number slider n, say from this is log n. This is just the exponent. Okay, because otherwise we have to log n. And then we set up, we should do nothing, and some go. So the idea is that The idea is that to report P of X, and this is exactly the unnormalized probability. So report X to the third divided by exp the X divided by T minus 1. Now this should be the desired probability distribution, normalized. Okay, so to set up, we do not essentially we do nothing. To go, okay, log n we don't need it. We go on until we stop. Allora, to go, maybe to set up, we can set up globals n, the energy, n equal to 0, set n 0. So to go, what should I do? So let maybe also globals n e pn, set pn 0, which is, we know that the probability of 0 is 0. So let p1, no, let y when 1 n plus, maybe we can put some dn, set dn 0.1. This is the fluctuations, so the movement of our sampling. We shall then tune this in order to have a quick convergence. So let this is the new energy plus random, say 2 times random flow at 1. This is from minus 1 and 1, no? Times dn. If an1 greater than 0, because less than 0 it is not possible, so we don't want to have no. If an greater than 0, what should we do? We should compute let p n1 p of n1, p of n1, if p an1. So now we have to accept the movement with the probability, which is pn1 over pan. So in order to do this, we use a Metropolis recipe. It says that if this is greater, we always accept. So if pn1 greater than pn, set an1, set pn1. Otherwise, we accept only with the probability equal to the ratio, or random flow at 1 less than pan over pan1. Should be like this, no? Because in this case at the first I should always accept, because this is true.
Yeah.
But if it is this is less than this, no, so this is pen 1 divided by pen. Because this is less, this is always a probability, no? Because this is, in this case, this is less than this, so this is less than 1, so with a given probability. So, for instance, suppose that pen is very large and pen 1 is small, so this is not true. This can be true with a small probability.
Okay.
And then I have to take to put this into some list. So list L. Set L an empty list. L put L n. And that's all. Maybe I can reset ticks. Here I tick and say if ticks mod 1000 equals 0, histogram L. So we don't need this, we need just a plot. X max, okay, let's try with say some small value of temperature. Maybe we can just save it before. Save black body. Oh, something. Globals should be before probably. Okay, clear this. I need an end. L put set L put because I cannot alter. Check. Okay. Setup. Go. L put input to be a list. But got setup. Go no. Probably it is the opposite, as always. Okay. Number too large, which probably is exponential. This T5. Well, maybe we can just show and just to see what happens. Go. It seems to increase always. Yes, sure. No, flat -1. No, because this is a number from 0 to 1. This is a number from 0 to 2. And this is a number from -1 to 1. Otherwise, clearly it always increases. Let's try again. Okay, so it stays more or less limited. Now we can remove the show. It increases too much. But maybe it is just the limit. We have also to change this to bar. Not so bad, because it resembles a bit the black body spectrum.
Yes, it is. And I think it's even closer to the sun distribution.
No, yes, but we have not implemented the windows.
Yeah, I know, but it looks
transparency.
very much like the sun one.
Yes, but we have to wait a bit. Maybe we can increase this in order to allow larger fluctuations and check if it is now. You see that
Yes.
now it is no, it resembles a bit no the black body radiation. No,
Yes.
now we actually have you studied the Monte Carlo simulations, Lucille?
I'm not planning to do any simulations at first.
No, but just for
My is
related
more
this kind of things.
experimental.
This kind of thing. Okay, in case if you want to use this, the idea here now is that we should compute the acceptance rate, because in this in any kind of Monte Carlo simulation you have to propose a movement and to accept or not to accept. The best convergence is when you accept half of the movement, because if you accept all the movement, you are losing the sampling, because you are moving essentially, you are just taking the random numbers. If you accept all this random number here, so you have a flat distribution. If you are refusing everything, you are not moving. So the best is to have the acceptance rate. No, so let's monitor the acceptance rate so that we can tune this. Maybe this can be put as a slider, so we can check DAN. Maybe 0.01 up to, I don't know, 4. 0.01, I don't know. Then we can check. Now we want to monitor the acceptance rate, which is A over X. And then we set A 0, and every time we accept the move, set A plus 1. Set. So let me see. Go. Okay, probably this is too high. Let me see what happens if I reduce too high. So probably we can increase this more. Huh? So let me. You see now it reduces, but we can increase a lot. Now it is too small. So now we can check how the shapes approximate the right one by changing this. So for instance, if we put this to say 8, it is a 0.8 the acceptance rate, which is already good. Essentially should not be 0.01 or 0.999. So let's try. If we put very, very small, you see that it takes a lot of time in order to reach the asymptotic distribution, because the acceptance rate is too high in this moment. No, because it is always accepted because it tries to move. If this is too big, the accept, maybe we can increase it or more. Let me say 500. So if it is too big, we are performing jumps not too large. So we are going often in this tail, which has low probability, so it is not accepted. So you bounce back, and you don't accumulate enough statistics. No, you see. While if it is in this case, say probably the order of I don't know, 50, maybe. Clearly, we should wait a bit. Less, and this is about. Okay, you see that when it is sufficiently near to 0.5, it converges almost immediately to the right distribution. Okay, and so with this you can essentially generate any distribution without even normalizing it, which is also nice. You don't have to compute. It is an interesting application, no? And so with this you can generate all your photons, and clearly you can put in your. So let's suppose that now we want to have a hole so below a certain threshold, no? So if else value x less than, I don't know, 10, 0.001, so we want to have a flat, so point.
Qu'est-ce qu'il y a, Nyon? Ah, tu lui as dit quoi? Ah, merde. Ah bah du coup, tu dois passer par Gare du Nord. Ouais, vaut mieux. Demande-lui si je dois te passer un ticket de métro, de train ou pas. C'est vraiment si j'appelle maman, là? Non, vas-y. Le casque, Sorry, I was talking with...
I was trying to implement
my
also
brother.
the windows.
Yes, I saw.
So you see that you can have even a quite weird distribution, no? And still maybe we can put some larger value if you want here to have a small value here, and then your distribution. So you can do whatever you want. You can use any distribution, and
it's actually perfect for photovoltaic cells.
Yes, exactly. So I'm happy that I was able to furnish it, but clearly this is should be a known trick about Monte Carlo computation. But I realized that in many cases it is not like very much known. So okay, I think that this is the first step to generate photos, and then you have to do something with your photos.
Yeah. Yes. Well.
Okay. If you, I think that we can stop here because it is already, we have done a lot of things. It is not too late, but well, if you have other questions, I'm here at the Okay.
More with the language.
Yes. Okay.
Very interesting. Once again, I don't do tools, but it was very interesting to see that and to learn anything in addition to.
Actually, I'm preparing a course on statistical mechanics from a computational point of view using netlogo.
Okay.
So actually, most of these can also be found here, because it was a course that I gave during pandemics to the University of Gdansk. Should be this one. So if you are interested, here there are also some lessons about, say, chaos, so things like this. Now I'm writing a book on this. So if you're interested, go there and you'll find the news. Okay, Lucille?
Yes, thank you very much.
Okay, so let me know in the future if you do something or if you find something some that can be modeled using say netlogo. Interesting. Okay, and clearly let me know how you go on.
Well, we'll see if I have enough time to do simulation with netlogo because I'm already at the middle of my PhD. So yeah. But thank you very much.
Lucille, bye. And all
have
others
a nice weekend.
can watch this so in the future. And I think we can stop here for this course. Bye bye.
Bye.
Bye, sir.